Tonight's journey takes us somewhere most of us hope never to go, but somewhere our curious minds can't help but wander. We're exploring what would happen if you found yourself dying on every planet in our solar system. Not the quick deaths you see in movies, where bodies explode or freeze instantly. The real deaths. The ones based on actual physics, actual atmospheric conditions, and the unforgiving realities of planetary science. Before we begin this cosmic tour of mortality, take a moment to like this video if you're enjoying the content, and subscribe if you want more deep dives into the science of the universe, and let me know in the comments which planetary death sounds the most terrifying to you. Now, get comfortable. Maybe grab a warm blanket to remind yourself you're safe here on Earth, and let's explore the 8 different ways our solar system could end your existence. Our solar system is home to 8 major planets, each one a unique world with its own atmospheric composition, temperature profile, pressure conditions, and environmental hazards. From the scorched surface of Mercury, sitting barely 36 million miles from the Sun, to the frigid outer reaches of Neptune, nearly 2.8 billion miles away, each planet presents its own particular form of lethality. To understand how you would die on these worlds, we need to understand what keeps us alive here on Earth. Our bodies require a very specific set of conditions. We need breathable oxygen at about 21% concentration in our atmosphere. We need atmospheric pressure of about 1 bar, or 14.7 pounds per square inch at sea level, to keep our bodily fluids in their proper state. We need temperatures that generally stay between -40 and 130 degrees Fahrenheit for extended survival. We need protection from harmful radiation, which our magnetic field and ozone layer provide. Take away any one of these conditions, and the human body begins to fail. Take away all of them, and death becomes not a matter of if, but how quickly and how painfully. When exposed to the vacuum of space, contrary to what Hollywood shows us, you don't explode. Your skin is remarkably tough and elastic, capable of containing your body even in 0 pressure. You also don't instantly freeze, despite space being incredibly cold. Without air molecules to conduct heat away from your body, you lose thermal energy very slowly through radiation alone, at a rate of only about 100 watts, similar to a light bulb. What actually kills you in a vacuum is asphyxiation combined with ebullism. Here's what really happens. The moment you're exposed to vacuum, the air in your lungs rushes out. If you try to hold your breath, the pressure difference will rupture your lungs, forcing air bubbles into your bloodstream that can cause fatal embolisms. So the first rule of vacuum exposure is exhale immediately. With your lungs now empty of air, you have about 15 seconds before the deoxygenated blood reaches your brain, and you lose consciousness. During those 15 seconds, the water in your soft tissues begins to vaporize due to the absence of external pressure, a condition called ebullism. Your body swells to roughly twice its normal size. Your tongue might feel like it's boiling. Your eyes bulge but don't explode. After unconsciousness sets in, you have perhaps another 90 seconds before death becomes inevitable, as your organs shut down from oxygen deprivation. But that's just vacuum exposure, the baseline for understanding space death. Each planet in our solar system adds its own deadly twist to this formula. Some will kill you with crushing pressure, others with toxic chemistry, some with temperature extremes that make Earth's harshest environments look gentle. And one, our home, is the only place in the known universe where you could walk outside unprotected and not die within minutes. Let's begin our tour with the planet closest to our star, a scorched world of extreme temperature swings where the sun dominates the sky in a way that would terrify anyone who witnessed it. Imagine standing on Mercury. The first thing you'd notice, if you had the briefest moment to notice anything, is the sun. From Mercury's surface, our star appears almost 3 times larger than it does from Earth, dominating the sky with overwhelming brightness and power. The planet sits only 36 million miles from the Sun at its closest approach, less than 40% of Earth's distance. This proximity creates a world of extremes that would begin killing you in multiple ways simultaneously. Mercury has virtually no atmosphere. What it does have is technically called an exosphere, a region so thin it's barely distinguishable from vacuum. The surface pressure is less than 1/1,000,000th of Earth's atmospheric pressure. For all practical purposes, you're standing in space. This means that death from vacuum exposure begins immediately. But unlike the frigid void of deep space, you're also being bombarded by direct, unfiltered solar radiation, while standing on a surface that, depending on where you are, could be hotter than a kitchen oven or colder than Antarctic winter. Let's say you find yourself on Mercury's sun-facing side during the planet's sluggish day. Mercury rotates so slowly that one day on the planet lasts 176 Earth days, which means the sun crawls across the sky at an almost imperceptible pace. The surface temperature beneath your feet reaches 430 degrees Celsius, or about 800 degrees Fahrenheit. That's hot enough to melt lead, zinc, and tin. Hot enough that if you placed a pizza on the ground, it would char to ash in seconds. Your death would be a race between several competing processes. First, there's the vacuum exposure. As we discussed, you'd immediately begin losing consciousness from oxygen deprivation. But before that 15-second window even closes, the heat would be working its terrible magic. Your skin, directly exposed to 800 degree surface temperatures, would begin to burn immediately. Not the way you burn yourself on a stove where you can pull away. This would be full contact thermal exposure across your entire body, where it touches or faces the scorching ground and nearby rocks. The thermal radiation from the surface would cook you like food under a broiler. Your blood, rapidly boiling in the vacuum, would create vapor that tries to escape through your skin. The combination of extreme heat and vacuum would cause your body to desiccate at an alarming rate. The moisture in your eyes would evaporate almost instantly. Your mouth and throat would be seared dry, even as you gasp for air that doesn't exist. The proteins in your cells would denature, the same process that happens when you cook an egg, except happening throughout your entire body at once. Within those first 15 seconds before unconsciousness, you would experience perhaps the most excruciating pain imaginable. Your skin would be simultaneously freezing in some places where it faces away from direct sunlight, burning in others where thermal radiation strikes it, and splitting as the water in your tissues vaporizes. The pain receptors in your skin would be firing maximum distress signals to a brain that's rapidly running out of oxygen. But here's where Mercury adds another layer of horror: the radiation. Without an atmosphere or magnetic field to speak of, Mercury's surface is bathed in the full fury of solar radiation. Ultraviolet rays that would give you a sunburn on Earth in hours would be burning your exposed tissue in seconds. X-rays and other high-energy particles slam into you unimpeded. This radiation damage would be cooking you at the cellular level, shredding your DNA. But you wouldn't live long enough for that to matter. It's like worrying about cancer when you're already being cooked alive. After unconsciousness claims you, your body would continue its transformation. The extreme heat would char your skin black on the sun-facing side. The vacuum would continue to desiccate you, turning your corpse into something resembling a freeze-dried husk, except one side would be carbonized from the intense heat. Over the course of Mercury's long day, the sun would slowly move across the sky, and different parts of your body would take turns being roasted. The side facing away from the sun might experience some cooling, but cool on Mercury's day side still means temperatures well above what human tissue can withstand. Within a few hours, exposure to this environment would reduce an unprotected human body to little more than charred organic matter. The intense UV radiation would continue breaking down whatever complex molecules remained. Over Mercury's 176 Earth day long day, this process would continue until very little recognizable remained. But what if, instead, you found yourself on Mercury's night side? The planet's lack of atmosphere means it has no way to retain heat. As the sun sets, temperatures plummet catastrophically. The night side of Mercury reaches about negative 180 degrees Celsius, or negative 290 degrees Fahrenheit. This is colder than anywhere on Earth's surface, colder than the coldest winter night in Antarctica, approaching the temperature of dry ice. Your death on the night side would still begin with vacuum exposure. You'd still have those 15 seconds of consciousness, still experience the horrific sensation of your blood and tissues boiling in the absence of pressure. But instead of burning, you'd be freezing. The extreme cold would make your skin brittle even as it swelled from ebullism. The water vapour escaping from your tissues would freeze on contact with the near-vacuum environment, forming crystals on your skin. The freezing process would actually be slower than the burning process, simply because heat transfer in a vacuum is inefficient. You'd lose heat through radiation, but without air molecules to conduct the warmth away from your body, you wouldn't flash freeze the way you might imagine. Instead, over the course of several minutes after death, your body temperature would gradually drop. Your extremities, fingers and toes and nose and ears would freeze first, becoming rigid and brittle. The water in your cells would form ice crystals that would rupture cell walls. Eventually, over the course of hours, your entire body would freeze solid, becoming a grotesque sculpture of ice and flesh. Unlike the day side where solar radiation would break you down, the night side would preserve you quite well, at least until the sun rose again, 88 Earth days later. Then, as the Terminator, the boundary between day and night, crept across Mercury's surface, your frozen corpse would begin to thaw and then to cook, experiencing in sequence the same charring that would have happened had you died on the day side to begin with. Mercury offers no gentle deaths. Whether you die in scorching heat or frigid cold, whether solar radiation tears apart your DNA or whether you simply suffocate in the vacuum, this closest planet to our star is perhaps the most overtly hostile world in the inner solar system. It's a reminder that proximity to the Sun, our source of warmth and life, becomes a weapon when the protective barriers of atmosphere and magnetic field are stripped away. But as lethal as Mercury is, with its temperature extremes and radiation bombardment, it's not the hottest planet in our solar system. That distinction belongs to a world that, from Earth, appears as a brilliant point of light in the evening or morning sky, a world that ancient astronomers named after the goddess of love and beauty, with no idea of the hellish inferno that awaits beneath those bright reflective clouds. Venus has been called Earth's twin, and in some ways the comparison is apt. The two planets are similar in size, Venus being only slightly smaller. They're similar in mass and density. They orbit at similar distances from the Sun, with Venus at about 67 million miles compared to Earth's 93 million. From these facts alone, you might expect Venus to be at least somewhat hospitable. You would be catastrophically wrong. Venus is hell, not in the metaphorical sense, but in the most literal way a planet can embody that concept. It is, without exaggeration, the most hostile planetary environment in the inner solar system, more lethal even than Mercury despite being farther from the Sun. If you found yourself on Venus's surface without protection, you would die in ways that would make Mercury's quick roasting seem almost merciful by comparison. Let's start with the atmosphere, because Venus's thick envelope of gas is what creates this hell world. The atmosphere is 96.5% carbon dioxide, with clouds composed not of water vapour, but of sulfuric acid. Yes, sulfuric acid, the same chemical used in car batteries and industrial processes. These droplets form thick cloud layers that completely shroud the planet, reflecting about 75% of the sunlight that reaches them. This is why Venus appears so bright from Earth. But those reflective clouds aren't protecting the surface. They're trapping heat in the most extreme greenhouse effect ever observed on a terrestrial planet. The atmospheric pressure at Venus's surface is 93 times that of Earth at sea level. 93 times. To experience equivalent pressure on Earth, you would need to dive about 3,000 feet or nearly 900 meters beneath the ocean surface. The weight of Venus's atmosphere would crush you even before the other killing mechanisms had their chance. But let's walk through your death on Venus step by step, because it's a symphony of simultaneous lethality. Imagine you're suddenly transported to Venus's surface. The first thing you'd feel, in the split second before pain overwhelms all sensation, is the pressure. 93 Earth atmospheres of force pressing on every square inch of your body from all directions. Your chest would be unable to expand to draw breath. The air in your lungs would be compressed to a fraction of its normal volume. Your eardrums would rupture immediately. The soft tissues of your body, your eyes, your sinuses, your internal organs would all be compressed by this tremendous force. But you wouldn't have time to fully process this, because you'd simultaneously be experiencing the temperature. Venus's surface temperature is 462 degrees Celsius, or 864 degrees Fahrenheit. This is hot enough to melt lead, zinc, and tin. It's hotter than the melting point of many metals. It's hot enough that some spacecraft components designed for Venus landers have failed simply from heat exposure, even with the best thermal protection engineering can devise. Your skin would begin charring within seconds. Not just burning, but actually carbonizing like wood in a fire. The proteins in your cells would denature instantly. Your blood, still under that tremendous pressure, wouldn't boil as it would in vacuum, but it would rapidly heat to temperatures that would cook you from the inside. Let's talk about what happens to human tissue at 864 degrees Fahrenheit. At about 160 degrees, proteins begin to denature irreversibly. By 300 degrees, fat begins to render, and organs begin to fail catastrophically. At 864 degrees, you're well into the temperature range where organic matter doesn't just cook, it carbonizes and breaks down chemically. Your skin, your muscles, your organs, everything would begin to char black within moments, like meat left on a grill at maximum heat. And then there's the atmosphere itself. Remember, it's 96.5% carbon dioxide. There's no oxygen to breathe, not that breathing would be possible under this pressure and heat anyway. But carbon dioxide at this pressure and temperature becomes what's called a supercritical fluid, behaving like both a liquid and a gas. It would force its way into your lungs, not as breathable air, but as a suffocating, scorching fluid that would sear the delicate tissues of your respiratory tract. The sulfuric acid clouds above would occasionally rain down their corrosive droplets, though these drops would evaporate long before reaching the surface due to the intense heat. But there are other chemicals in Venus's atmosphere: hydrogen fluoride, hydrogen chloride, and sulfur dioxide, all of which are corrosive and toxic. At the surface concentrations and temperature, these chemicals would react with any moisture on your body, creating acids that would begin dissolving exposed tissue. Your eyes would be destroyed almost instantly, the fluids boiling away and the tissues corroding simultaneously. Let's estimate your timeline of death. In the first second, your eardrums burst from the pressure. Your lungs collapse as you're unable to exhale against 93 atmospheres of external force. The heat begins charring your skin. The pain for this first second would be beyond anything the human nervous system has evolved to process. Some scientists believe that extreme pain can actually cause the brain to shut down, a mercy mechanism against unbearable suffering. We might hope this would happen to you. By 5 seconds, you're almost certainly unconscious. The combination of oxygen deprivation, heat damage to your brain, and the massive trauma of pressure and burning would shut down consciousness. Your brain, like the rest of your body, would be cooking. The neurons would be dying en masse as proteins denature and cellular structures collapse. By 10 seconds, you're unquestionably dead. No human being could survive even a fraction of this exposure. Your heart would have stopped, likely from the direct heat damage to cardiac tissue, or from the pressure effects, or from both. Your blood, heated to temperatures far beyond what can sustain life, would no longer be circulating. The chemical composition of your body would already be changing as organic compounds break down in the heat. After death, your body would continue to cook and char. Within a few minutes, you would be reduced to little more than a carbonized husk. The intense heat would drive off water, breaking down organic molecules, reducing complex tissues to simpler carbon compounds and gases. Over the course of hours, what remained of your body would be further broken down by the corrosive atmosphere and the relentless heat. Some Soviet Venera landers that successfully touched down on Venus in the 1970s and 1980s lasted for only a short time before the heat and pressure destroyed their systems. The longest surviving lander, Venera 13, transmitted data for just 127 minutes before succumbing, and these were heavily armoured spacecraft designed specifically to withstand Venus's environment. An unprotected human body wouldn't last a tiny fraction of that time. Venus teaches us that planetary habitability isn't just about distance from the Sun. It's about the delicate balance of atmospheric composition, magnetic fields, geological activity, and countless other factors. Venus probably had oceans billions of years ago. It might have been habitable once, but a runaway greenhouse effect turned it into the hell world we see today, where surface temperatures exceed those of Mercury despite being nearly twice as far from the Sun. If Mercury kills you with radiation and temperature extremes, Venus kills you with heat, pressure, and chemical toxicity all at once. It's a reminder that our pale blue dot, hanging in space at just the right distance from the Sun with just the right atmosphere, is far more precious and rare than we often appreciate. Because just one planet over, 26 million miles closer to the Sun, conditions shift from habitable to absolutely lethal. Let's move outward now, past Earth, to the next planet in line, a world that has captured human imagination for centuries. The Red Planet, named for the god of war, a cold desert world that might seem almost welcoming compared to Venus's inferno, but which harbours its own particular ways to end your life. Mars has long been humanity's best candidate for extraterrestrial colonisation. It appears in countless science fiction stories as a place where humans might one day live, work, and thrive. Orbital probes and rovers have shown us a world that seems almost familiar: canyons and volcanoes, polar ice caps and dust storms, ancient river valleys that speak of a wetter past. But Mars's apparent familiarity is deceptive. The Red Planet is a frozen desert with an atmosphere so thin it's barely there, and while it would kill you more slowly than Venus or Mercury, it would kill you nonetheless, through a combination of suffocation, freezing, and decompression. The Martian atmosphere is about 0.6% as dense as Earth's atmosphere at sea level. To put that in perspective, if you stood at the summit of Mount Everest, where atmospheric pressure is about 1/3 of sea level pressure, and climbers need supplemental oxygen to survive, you'd still be experiencing atmospheric pressure more than 50 times higher than what you'd find on Mars's surface. The Martian atmosphere is so thin that it's essentially a partial vacuum. This atmosphere is 95.3% carbon dioxide, with small amounts of nitrogen and argon, and trace amounts of oxygen. There's essentially no breathable air whatsoever. The average surface pressure is only about 600 pascals, or 0.6% of Earth's atmospheric pressure. This creates immediate problems for an unprotected human. Imagine you're standing on Mars's surface near the equator on a relatively warm afternoon. The local temperature might be as high as 20 degrees Celsius, or about 70 degrees Fahrenheit. If you could somehow breathe, you might initially think the temperature isn't so bad. But within 1 or 2 seconds of exposure, you'd realise the terrible truth of Mars's thin atmosphere. In pressure this low, the boiling point of water drops dramatically. At Mars's surface pressure, water boils at just above degrees Celsius. This means that the moisture on your tongue, in your eyes, in your mouth and lungs would immediately begin to boil. You'd experience the same ebullism we discussed for vacuum exposure, though slightly less severe because there is some atmospheric pressure. The saliva on your tongue would foam and bubble. The moisture in your eyes would evaporate rapidly, and you'd feel a burning, freezing sensation as that evaporation drew heat from the surrounding tissues. You'd try to breathe, an automatic reflex, but there's nothing to breathe. The thin carbon dioxide atmosphere would rush into your lungs, but it would provide no oxygen whatsoever. Within seconds, your blood oxygen levels would begin to plummet. The carbon dioxide in the air might actually enter your bloodstream, contributing to hypercapnia, carbon dioxide poisoning, though oxygen deprivation would kill you long before CO2 poisoning became the main concern. Meanwhile, the low pressure would cause your body to swell as gases in your tissues expanded. You'd bloat visibly, though your skin is tough enough to prevent rupturing. The nitrogen dissolved in your blood would come out of solution, forming bubbles, the same process that causes decompression sickness in scuba divers who ascend too quickly. These bubbles would block blood flow, contributing to tissue damage and organ failure. Your timeline to unconsciousness would be similar to vacuum exposure, about 15 seconds as deoxygenated blood reaches your brain. During those 15 seconds, you'd be aware of the pain in your eyes and mouth from the rapid evaporation, the tightness in your chest as you fail to get oxygen, and the swelling of your body. You might stagger, disoriented, as your brain began to shut down from hypoxia. Once unconscious, you'd have perhaps 90 seconds before death became irreversible, just like in vacuum. Your heart would continue beating for a short time, trying valiantly to circulate blood that contained no oxygen to tissues that were rapidly dying. Eventually, cardiac arrest would follow, brought on by the combination of hypoxia, pressure trauma, and the breakdown of normal physiological processes. But we're not done yet because we haven't addressed temperature. While a Martian afternoon near the equator might reach 70 degrees Fahrenheit, that's a brief peak. Mars's average surface temperature is about -60 degrees Celsius, or -80 degrees Fahrenheit. And at night, or at higher latitudes, temperatures can plunge to -125 degrees Celsius, or -195 degrees Fahrenheit. With such a thin atmosphere, Mars has no ability to retain heat. When the sun sets, temperatures drop catastrophically. If you died on Mars during the day, your body would still be there when night fell, and over the course of that Martian night, which lasts about 12.5 hours, you would freeze solid. The process would be faster than on Mercury's night side, because Mars's atmosphere, thin as it is, still provides some thermal conductivity to draw heat away from your body. The freezing would be thorough. Water in your cells would form ice crystals, rupturing cell membranes and destroying tissue structure. Over multiple day-night cycles, freeze-thaw damage would break down your body at the cellular level. But Mars's cold and dry environment would also preserve you remarkably well. Without liquid water and with minimal atmospheric oxidation, decomposition would be incredibly slow. Your frozen, desiccated corpse could remain recognizable for decades or even centuries, a grotesque monument to the planet's lethality. There's one more way Mars could kill you, or at least make your death more unpleasant. Dust storms. Mars experiences dust devils and larger dust storms regularly. Every few years, these storms can grow to encircle the entire planet. The dust particles are extremely fine, much finer than Earth sand, and they would coat every surface. If you were still alive when a dust storm hit, the dust would irritate your eyes, nose, and throat. The particles would enter your lungs as you gasped for air you couldn't get anyway. And some Martian dust may contain perchlorates, toxic compounds that could damage tissue they came in contact with. But let's be honest, the dust storm would be the least of your concerns. You'd be dying from asphyxiation and decompression trauma long before the dust became a significant problem. Radiation is another long-term hazard on Mars. The planet has no magnetic field and only a wispy atmosphere, so solar and cosmic radiation reaches the surface largely unimpeded. You'd be exposed to radiation doses that would cause radiation sickness and cancer over time. But again, you'd be dead from suffocation within minutes, so the radiation exposure, like the dust, would matter primarily to your corpse. Mars presents an interesting case study in planetary lethality. It's not overtly hostile in the way Venus is, with its crushing pressure and searing heat. it's not as immediately deadly as Mercury's radiation-blasted surface. At certain times and places, Mars's surface temperature can actually be quite pleasant, but the absence of breathable atmosphere and the extremely low pressure create conditions that would kill a human just as surely as the more obviously hostile environments of Venus or Mercury. Death would just take a minute or two rather than seconds. This is why Mars colonization, despite all the enthusiasm around it, would require massive technological infrastructure. Every human on Mars would need to live in pressurized, temperature-controlled environments with breathable air. Every excursion to the surface would require a full spacesuit. One breach, one failure of the life support system, and you'd have at most a minute or two to get to safety before death became unavoidable. But as we leave Mars behind and journey outward, we leave the realm of rocky planets entirely. Beyond Mars's orbit lies the asteroid belt, and beyond that the giants. Worlds so massive that Earth would fit into them many times over. Worlds without solid surfaces, where atmospheric pressure doesn't stop at 93 bars like Venus, but continues climbing until it reaches pressures that would crush the hardest substances we know. Let's venture into the realm of Jupiter, king of the planets, and discover what death looks like when you fall into an endless sky. Jupiter is colossal. It's 11 times wider than Earth. Its mass is 318 times Earth's mass. It could swallow all the other planets in the solar system combined and still have room left over. When you look at Jupiter through a telescope, you see those distinctive bands of colour. The creams and oranges and browns, the swirling storms, the famous Great Red Spot that has been raging for at least 300 years and is larger than Earth itself. It's beautiful in an alien forbidding way, but Jupiter has no surface. There's no ground to stand on, no solid rock beneath your feet. What you see when you look at Jupiter are the tops of cloud layers, marking the altitude where atmospheric pressure equals about one Earth atmosphere. But that's not a surface in any meaningful sense. It's just the point where the atmospheric pressure happens to match ours. Below those visible clouds, the atmosphere simply gets denser and denser, transitioning eventually from gas to liquid and then, in the deep interior, to exotic forms of matter unlike anything found on Earth. So your death on Jupiter wouldn't be like death on the terrestrial planets. You wouldn't land on solid ground. Instead, you'd fall, and fall, and fall, until the increasing pressure and temperature killed you in ways that would be frankly spectacular. Let's imagine you're somehow positioned in Jupiter's upper atmosphere, at an altitude where the pressure is similar to Earth's and the temperature is tolerable, perhaps around 165 Kelvin, or negative 108 degrees Celsius. You'd be surrounded by hydrogen and helium gas, the two elements that make up most of Jupiter's mass, with trace amounts of methane, ammonia, water vapour, and other compounds. The sky above you would be mostly clear, but around you would be the colourful clouds of ammonia ice crystals that give Jupiter its banded appearance. You can't breathe here. The atmosphere is hydrogen and helium with no oxygen, so you'd begin suffocating immediately following the familiar timeline, about 15 seconds to unconsciousness, 90 seconds until death is irreversible. But unlike on Mars or in vacuum, you wouldn't just fall unconscious and die. Because you're falling. Jupiter's gravity is 2.5 times Earth's. That means you'd be falling with an acceleration 2.5 times what you experience on Earth. The fall would be fast and would keep getting faster. As you descended, you'd pass through different cloud layers. First, the ammonia ice clouds. Below those, at higher pressures and temperatures, clouds of ammonium hydrosulfide. Below those, water clouds. The colours would be spectacular if you were conscious to see them. Swirls of brown and orange and white, bands stretching around the entire planet, turbulent zones where gases rise and fall in complex circulation patterns driven by Jupiter's rapid rotation and internal heat. But the real killing would begin as the pressure mounted. At a depth where the pressure reaches about 10 bars, 10 times Earth's sea level pressure, your eardrums would have long since ruptured. Any gas spaces in your body would be compressed. Your lungs, if they weren't already collapsed from lack of oxygen, would be squeezed smaller. The increasing pressure would force gas into your tissues and bloodstream, descend deeper, and the pressure continues to climb. At 100 bars, 100 times Earth's pressure, the hydrogen and helium around you would be getting noticeably denser. You'd be about 90 kilometers below the visible cloud tops. The temperature would be rising too as gravitational compression heats the atmosphere. Perhaps 340 Kelvin now, or about 67 degrees Celsius, 150 degrees Fahrenheit. Keep falling. At 1,000 bars, the temperature is now well over 1,000 Kelvin, 700 degrees Celsius or more. The pressure is crushing. To put 1,000 bars in perspective, the deepest parts of Earth's oceans experience about 100 bars of pressure. Your body would be compressed to a fraction of its normal volume. Bones would begin to crack and splinter under the force. Organs would be pulped. Any remaining gas spaces would be compressed to vanishingly small volumes. But you'd keep falling, because there's still no bottom. The pressure continues to build. At around 2 million bars, roughly 2 million Earth atmospheres, something extraordinary happens to the hydrogen around you. Under this immense pressure, and at temperatures around 10,000 Kelvin, hydrogen atoms are squeezed so tightly that their electrons are stripped away. The hydrogen transitions from a molecular gas or liquid into a state called liquid metallic hydrogen, where it can conduct electricity like a metal. This is the material that generates Jupiter's immense magnetic field. Long before you reach this depth, you would be dead. Not just dead, but crushed into a compressed mass of organic material, heated to thousands of degrees, subjected to pressures that would alter your chemical structure. The carbon, nitrogen, oxygen, and other elements that made up your body would still exist, but they wouldn't be organized into anything resembling a human being anymore. You'd be reduced to a compressed slurry of elements sinking ever deeper into Jupiter's interior. At the very center of Jupiter, pressures might exceed 45 million Earth atmospheres. Temperatures could reach 30,000 Kelvin or higher. If Jupiter has a solid core, which is still debated among planetary scientists, it would be composed of exotic materials, hydrogen compounds and rock compressed into forms that don't exist anywhere on Earth's surface. But let's back up and think about your death in more detail. At what point would you actually die? You'd be unconscious from hypoxia after about 15 seconds. If we assume you started at an altitude with pressure around 1 bar, you'd be falling at increasing speed due to Jupiter's powerful gravity. Within a minute or two of unconscious falling, you'd descend to depths where the pressure and temperature became lethal. Perhaps at 10 or 20 bars of pressure and temperatures approaching 100 degrees Celsius, your body would begin to shut down not just from lack of oxygen, but from direct heat damage and pressure trauma. The interesting, or perhaps horrifying aspect of death by gas giant is that there's no moment of impact, no sudden stop. It's a continuous descent into increasingly lethal conditions. You transition from merely uncomfortable to dead to destroyed to chemically altered, and the process would take hours or perhaps even days depending on the details of your trajectory and how we define you at each stage. Jupiter's winds, which can exceed 360 miles per hour in some regions, would buffet you during your descent. You might be caught in the Great Red Spot, a storm system larger than Earth where winds circulate around a high-pressure centre. But wind speed would matter less and less as the atmosphere around you became denser and denser, eventually transitioning to conditions more like falling through very dense fluid than falling through air. One blessing, if we can call it that, is that you'd be unconscious for most of this ordeal. The hypoxia-induced unconsciousness would claim you long before the pressure and heat reached truly excruciating levels. Your last conscious moments would be spent gasping for breath in an atmosphere of hydrogen and helium, falling through alien clouds toward an abyss that has no bottom. Jupiter kills you not with a single catastrophic event, but with a gradual escalation of pressure and temperature, crushing and cooking you simultaneously as you sink into the planet's interior. It's death by descent into an increasingly hostile environment with no possibility of stopping or turning back. Your atoms would end up mixed into Jupiter's atmosphere and interior, eventually participating in the convection currents that drive the planet's complex weather systems. In a sense, you'd become part of Jupiter, your matter distributed throughout the gas giant's vast bulk. As we leave Jupiter behind, we encounter a world that in many ways is similar to Jupiter, but also distinctly different. A planet famous for its spectacular ring system, a world of pastel colours and hexagonal storms, where winds blow even faster than on Jupiter, and the atmosphere transitions to liquid at a deeper level than on Jupiter due to lower internal pressure. Saturn is the second largest planet in our solar system, and in many ways it's Jupiter's smaller, less massive sibling. Its composition is similar, mostly hydrogen and helium with trace amounts of other gases. Like Jupiter, it has no solid surface but rather a continuous atmosphere that gets denser with depth until it transitions to liquid. Like Jupiter, it has powerful winds and complex weather systems. But Saturn has some unique features that would affect how you die there. The most obvious difference is Saturn's spectacular ring system, those thin bands of ice and rock particles that circle the planet's equator. If you somehow found yourself falling towards Saturn from above or below its orbital plane, you might pass through the rings. The rings are thin, typically only about 30 feet thick despite being tens of thousands of miles across. But they're made of countless particles ranging from grain-sized to house-sized chunks of ice and rock. Passing through the rings would be like being caught in a cosmic hailstorm moving at orbital velocities. Particles would impact you at speeds of thousands of miles per hour. Each impact would be devastating. Even a small piece of ice hitting you at these velocities would punch through your body like a bullet. Larger chunks would simply tear you apart. You'd be shredded by innumerable impacts, your body reduced to a cloud of organic debris that would join the ice and rock already orbiting the planet. This would be death by cosmic sandblaster, extraordinarily violent but mercifully quick. But let's assume you somehow avoided the rings and found yourself descending into Saturn's atmosphere. The process would be similar to falling into Jupiter, but with some important differences. Saturn's atmosphere, at the visible cloud tops, has temperatures around negative 178 degrees Celsius, about negative 288 degrees Fahrenheit. It's colder than Jupiter's upper atmosphere because Saturn is farther from the Sun and receives less solar energy. As on Jupiter, you'd suffocate in the hydrogen-helium atmosphere within a minute or two of unconsciousness. You'd begin falling, accelerated by Saturn's gravity, which is slightly weaker than Earth's at 1.065 times our surface gravity, but still substantial. The winds on Saturn are fierce, among the fastest in the solar system. Near the equator, winds can reach 800 kilometers per hour, or about 118 miles per hour. These supersonic winds would toss you around like a leaf in a hurricane, tumbling and spinning as you descended. The cloud structure on Saturn is similar to Jupiter's. Upper clouds of ammonia ice, lower clouds of ammonium hydrosulfide, and deeper still, water clouds. But Saturn's clouds are hazier and less distinct than Jupiter's, giving the planet a more muted pastel appearance. The famous hexagon at Saturn's North Pole, a jet stream in the shape of a perfect hexagon, is large enough to fit 4 Earths across. If you fell through this region, you'd be caught in these geometric winds, though you'd be unconscious and wouldn't appreciate the strangeness of it. As you descended deeper into Saturn, pressure and temperature would increase, though not quite as rapidly as on Jupiter, because Saturn's lower mass means less gravitational compression. At about 1 million bars of pressure and temperatures reaching several thousand Kelvin, the hydrogen around you would transition to metallic hydrogen, just as it does in Jupiter, but this transition would occur at a deeper level on Saturn. The crushing process would be the same. Your body would be compressed, heated, and eventually broken down into its constituent elements. The timeline might be slightly longer than on Jupiter because of Saturn's weaker gravity and less steep pressure gradient, but the end result would be identical. You'd be reduced to a compressed mass of organic elements, distributed throughout the planet's interior. One interesting feature unique to Saturn is its extremely low density. Saturn's overall density is less than that of water. If you could find a bathtub large enough, Saturn would float. This low density comes from Saturn's low mass relative to its size, meaning the hydrogen and helium are less compressed than in Jupiter. But don't let that fool you. The pressures in Saturn's interior are still millions of times Earth's surface pressure, more than sufficient to crush any possible material into exotic forms. Saturn also radiates more heat than it receives from the Sun, just like Jupiter, though the mechanism might be different. Jupiter's heat comes from gravitational contraction, the planet slowly shrinking and releasing potential energy. Saturn might have an additional heat source, helium rain. Deep in Saturn's interior, helium might condense into droplets that fall like rain through the liquid hydrogen, releasing energy as they descend. If this theory is correct, your falling body would eventually encounter a region where helium droplets are constantly precipitating downward, though at that depth you'd be long dead, and your remains would be thoroughly crushed and heated beyond recognition. Your death on Saturn would be essentially identical to your death on Jupiter. Suffocation, followed by an endless fall, through increasingly dense and hot atmospheric layers, culminating in pressure-induced destruction and chemical breakdown. The main differences would be the possible encounter with the ring system, the stronger winds, the colder initial temperature, and perhaps a slightly longer timeline due to weaker gravity. But the end result is the same. Saturn, like Jupiter, would reduce you to atoms distributed throughout its vast atmosphere and interior. Let's continue our journey outward now, leaving Saturn behind and venturing into the realm of the ice giants. These planets are smaller than Jupiter and Saturn, but larger than Earth. They have atmospheres of hydrogen and helium, but also significant amounts of water, methane and ammonia ices in their interiors. They're worlds of peculiar characteristics, including one planet that spins on its side and another that boasts the fastest winds in the solar system. Uranus is strange. Not just strange in the casual sense, but genuinely bizarre by planetary standards. At some point in its past, Uranus was knocked onto its side, probably by a massive collision during the solar system's formation. Now, its axis of rotation is tilted 98 degrees relative to its orbital plane. This means Uranus essentially rolls around the Sun on its side. During its 84-year orbit, each pole gets 42 years of continuous daylight, followed by 42 years of continuous darkness. No other planet in the solar system exhibits this extreme behaviour. This unusual orientation affects its weather and atmospheric circulation in ways that aren't fully understood. But from the perspective of someone dying there, Uranus's tilt is less important than its other characteristics. Extreme cold, a hydrogen-helium-methane atmosphere, winds that can reach 560 miles per hour, and the lack of any solid surface. Uranus's upper atmosphere is the coldest in the solar system, with temperatures dipping to 49 Kelvin, or negative 224 degrees Celsius, negative 371 degrees Fahrenheit. This is colder than Neptune despite Uranus being closer to the Sun, a mystery that might be explained by Uranus's lack of a significant internal heat source. While Jupiter, Saturn and Neptune all radiate more energy than they receive from the Sun, Uranus radiates only about as much as it receives, suggesting its interior is cold and inactive compared to the other giants. If you found yourself in Uranus's upper atmosphere at an altitude where pressure was similar to Earth's, you'd be surrounded by hydrogen and helium gas with about 2.3% methane. This methane is what gives Uranus its pale blue-green colour. Methane absorbs red light, so when sunlight bounces off Uranus's cloud tops and back into space, it's predominantly blue and green wavelengths that escape. You'd suffocate in this atmosphere within the usual timeline, about 15 seconds to unconsciousness, but the extreme cold would be working on you simultaneously. At negative 224 degrees Celsius, any exposed skin would begin to freeze almost instantly. The moisture in your eyes, nose and mouth would freeze solid within seconds. Your extremities, fingers and toes and ears would become brittle and fragile. If you tried to move, they might snap off. As you began to fall into Uranus's depths, you'd pass through cloud layers. Unlike the colourful clouds of Jupiter and Saturn, Uranus's clouds are subtle and hard to see. There's a layer of methane ice clouds, and possibly lower layers of hydrogen sulfide and ammonia clouds, but these aren't as distinct or dramatic as the clouds on the larger gas giants. The atmosphere is hazy and relatively featureless, which is why telescopic images of Uranus often show it as a nearly uniform pale blue disk. The winds on Uranus are fast but not as organised as on Jupiter or Saturn. They blow mostly in the direction of rotation near the equator, reaching 560 miles per hour, then shift to blowing opposite the rotation near the poles. You'd be buffeted by these winds as you fell, but the low temperature would already have frozen you solid if you weren't dead from hypoxia. As you descended deeper, pressure and temperature would increase. Uranus is called an ice giant because its interior is thought to consist primarily of water, methane, and ammonia ices under high pressure, rather than the hydrogen and helium that dominate Jupiter and Saturn. These ices aren't ice in the familiar sense. Under the pressures and temperatures deep in Uranus, they exist as hot, dense fluids. Descend to a depth where pressure reaches thousands of bars and temperature climbs to 5,000 Kelvin or higher. The hydrogen and helium would transition to a supercritical state, neither quite gas nor quite liquid. Deeper still, you'd reach the layer of water, methane and ammonia, compressed into exotic ices that can conduct electricity. Some models suggest that deep in Uranus, at pressures around 800,000 times Earth's sea level pressure, methane might be split apart by the pressure, with the carbon atoms crystallizing into diamond. Yes, it might literally rain diamonds in Uranus's interior, solid diamond crystals falling through a sea of hydrogen. Your body would not survive to see these diamond rains. Long before you reach such depths, the pressure would have crushed you, and the temperature would have cooked your remains. The timeline would be similar to Jupiter and Saturn, though perhaps with a slightly less steep pressure gradient because Uranus is smaller and less massive. But the end result is the same: reduction to atoms distributed through the planet's atmosphere and interior. One unique aspect of death on Uranus is that, because of its sideways tilt, the experience might differ depending on when in Uranus's year you arrived and where you fell into the atmosphere. If you entered during one of the long polar nights, you'd be falling through darkness, with no sunlight to illuminate the clouds and hazes around you. If you entered during polar summer, you might be falling through continuous dim daylight for hours as you descended. But these are aesthetic differences. The lethality would be the same. Uranus would kill you with cold, suffocation, and eventually pressure and heat, just like the other gas giants, but it would do so in a quieter, more subtle way. There are fewer dramatic storms, less striking colours, cooler initial temperatures. It's death by descent into a cold, featureless abyss. Compared to the vivid deaths on Venus or Jupiter, death on Uranus would be almost boring if death can be boring. You'd freeze, suffocate, and eventually be crushed and heated into oblivion, all while surrounded by pale blue haze and little else. But there's one more giant planet to visit, the last of the major worlds in our solar system. A planet discovered through mathematical calculation before it was seen with telescopes. A deep blue world where winds scream at supersonic speeds and storms larger than Earth rage in the frozen atmosphere. Let's descend into Neptune's cold fury and complete our tour of planetary deaths. Neptune is the 8th and final major planet in our solar system, orbiting the Sun at an average distance of 2.8 billion miles. At this distance, sunlight takes over 4 hours to travel from the Sun to Neptune. The Sun appears as little more than a very bright star in Neptune's sky, providing very little warmth, and yet Neptune is an active world with violent weather, powered not by the Sun but by heat from its interior. Neptune is similar in size and composition to Uranus. It's slightly smaller but slightly more massive, making it denser. Like Uranus, it's an ice giant with an atmosphere of hydrogen, helium and methane surrounding an interior of water, methane and ammonia ices. But unlike Uranus, Neptune has a significant internal heat source. It radiates about 2.6 times more energy than it receives from the Sun. This internal heat drives incredibly fast winds and dramatic storms. The winds on Neptune are the fastest in the solar system. They can reach 2,100 kilometers per hour, or about 1,300 miles per hour. That's faster than the speed of sound in Earth's atmosphere. These are supersonic winds, creating shock waves as they blow through Neptune's atmosphere. If you fell into Neptune, these winds would batter you with unimaginable force, tumbling you through the sky as you descended. Neptune's atmosphere, at altitudes where pressure is around 1 Earth atmosphere, has temperatures around 55 Kelvin or negative 218 degrees Celsius, negative 360 degrees Fahrenheit. This is slightly warmer than Uranus, despite Neptune being farther from the Sun, evidence of Neptune's internal heat. But warmer is relative. It's still cold enough to freeze any terrestrial substance solid. As on Uranus, the methane in Neptune's atmosphere absorbs red light, giving the planet a striking blue colour. But Neptune's blue is deeper and more saturated than Uranus's pale blue-green. The exact cause of the richer colour isn't fully understood, but might involve additional atmospheric components or different concentrations of methane at various altitudes. If you found yourself falling into Neptune's atmosphere, you'd experience the now familiar suffocation in a hydrogen-helium-methane mixture. You'd lose consciousness within 15 seconds. But unlike the relatively calm fall on Uranus, your descent through Neptune's atmosphere would be violent. The supersonic winds would slam into you, accelerating you, decelerating you, spinning you around. The turbulence would be extraordinary. You'd be frozen solid from the extreme cold, your corpse tumbling through the clouds like an ice sculpture in a hurricane. Neptune has visible storm systems. The Great Dark Spot, observed by Voyager 2 in 1989, was a storm system similar in some ways to Jupiter's Great Red Spot, though it has since dissipated and new dark spots have appeared elsewhere on the planet. These storms are high-pressure systems where clouds rise higher into the atmosphere than surrounding regions. If you fell through one of these storms, the turbulence would be even more extreme, the winds even faster. As you descended deeper into Neptune, the pressure would build and the temperature would rise. Neptune's interior structure is thought to be similar to Uranus, layers of hydrogen and helium transitioning to a mantle of water, methane and ammonia ices under high pressure, and possibly a rocky icy core at the centre. Like Uranus, Neptune might have diamond rain in its interior, carbon from methane crystallizing under extreme pressure and falling as solid diamonds through the fluid mantle. The pressure at Neptune's core might reach 7 million Earth atmospheres, with temperatures around 5400 Kelvin or 9300 degrees Fahrenheit. These are conditions that would, as with all the gas and ice giants, crush and heat your body into a compressed mass of atoms. The timeline would be similar to Uranus, perhaps slightly faster due to Neptune's higher mass and density. Your death on Neptune would combine the extreme cold and suffocation of Uranus with the violent winds and turbulence unique to this distant world. You'd freeze, suffocate, be battered by supersonic winds, and then crushed and heated as you descended into the planet's depths. It would be a chaotic, violent end, your frozen corpse tumbling through blue clouds before being destroyed by forces that would reduce you to your constituent atoms. Neptune represents the outer boundary of our tour. Beyond Neptune lie dwarf planets like Pluto and other Kuiper Belt objects, but we've covered the 8 major planets, from scorching Mercury to frozen Neptune, from the thin vacuum of Mars to the crushing depths of Jupiter. Each planet offers its own unique form of death, its own combination of temperature, pressure, chemistry and radiation that would kill an unprotected human. But having completed this tour, let's step back and compare these deaths. Which would be fastest? Which would be slowest? Which would be most painful? And what does this tour of mortality teach us about the incredible rarity and preciousness of Earth, the only known world where we can walk outside without protection and not die within minutes. We've journeyed through our solar system, witnessing 8 different ways to die on 8 different worlds. Each death was unique, shaped by the specific conditions of each planet. But now let's compare these deaths directly, analysing them along several dimensions: speed of death, degree of pain, violence of the process, and what would happen to your body afterward. Let's start with the speed of death, measured as the time from exposure to loss of consciousness and then to irreversible organ failure. On Mercury, whether day side or night side, you'd lose consciousness within about 15 seconds from vacuum exposure, with death following within 90 seconds. The extreme heat or cold would add additional trauma, but the timeline would be dominated by the suffocation. On Venus, you'd likely lose consciousness within 1 to 5 seconds due to the combination of crushing pressure, extreme heat, and toxic atmosphere. Death would be essentially instantaneous by planetary standards. Your brain would cook in seconds, your organs would fail almost immediately, and you'd be dead before 10 seconds had passed. Venus offers the fastest death in our survey. Mars would give you about 15 seconds to unconsciousness, just like vacuum exposure on Mercury, with death following in the next 90 seconds. The low pressure would cause ebullism and oxygen deprivation, killing you in a timeline similar to Mercury's. On Jupiter, Saturn, Uranus and Neptune, the initial timeline would be the same: 15 seconds to unconsciousness from oxygen deprivation, followed by death within 90 seconds. But unlike the terrestrial planets where you'd simply collapse and die, on the gas giants you'd continue falling into increasing pressure and temperature even after death. Your body would be destroyed over the course of minutes to hours as you descended into the crushing depths. So Venus wins, or loses depending on your perspective, for fastest death, probably less than 5 seconds to unconsciousness, less than 10 seconds to death. Mars and Mercury tie for the next fastest, both giving you about 15 seconds of consciousness. The gas giants all offer the same initial timeline, but with the prolonged destruction of your corpse afterward. Now let's consider pain. Pain is subjective and difficult to quantify, but we can make some educated guesses. Venus would likely involve the most intense pain for the brief moment before your nervous system failed. The combination of extreme heat, pressure, and chemical burns would create a pain level beyond anything the human nervous system has evolved to process. However, this pain would last less than a second before shock and nervous system failure shut down your ability to feel anything. Mercury's dayside would involve severe burning pain as your skin charred, combined with the pain of ebullism as your tissues boiled. But you'd only experience this for about 15 seconds before unconsciousness. Mercury's night side would involve the pain of freezing combined with ebullism, a different quality of pain but probably similar intensity. Mars would involve the pain of ebullism and suffocation, but the somewhat higher pressure compared to pure vacuum might make this slightly less severe than on Mercury. It would still be agonizing, but perhaps marginally less so. On the gas giants, the initial pain would be from suffocation, and, on Uranus and Neptune, extreme cold. The descent and crushing would happen after you were unconscious, so you wouldn't feel the worst of it. This makes the gas giants perhaps the least painful deaths, though that's a grim distinction. If we had to rank these deaths by pain, it might look like this: Venus, extremely intense but very brief; Mercury dayside, intense and lasting about 15 seconds; Mercury nightside and Mars, severe and lasting about 15 seconds; and the gas giants, moderate initial pain from suffocation and cold, but unconscious for the worst of the trauma. What about violence, defined as how dramatic and destructive the death would be? Venus wins again. You'd be simultaneously crushed, cooked, and chemically burned. Your body would be charred to a cinder within minutes. It's a violent, dramatic death. The gas giants would also be violent in their way, especially Neptune with its supersonic winds battering your corpse, but most of that violence would happen after you were unconscious and dead. Mercury's deaths would be violent in the sense of extreme temperature exposure, but less immediately destructive than Venus. Mars would be the least violent of the terrestrial planets, a relatively quiet suffocation and freezing. Now let's think about what would happen to your remains. On Venus, you'd be reduced to charred organic residue within hours, eventually broken down by the corrosive atmosphere. On Mercury's day side, you'd be desiccated and charred by heat and radiation, reduced to little more than carbon and mineral residue over the course of days. On Mercury's night side and on Mars, you'd freeze solid and be remarkably well preserved, potentially remaining recognisable for decades or centuries in Mars's cold, dry environment. On the gas giants, you'd be crushed and heated into atomic components, distributed throughout the planet's atmosphere and interior. Your atoms would participate in the planet's convection currents, perhaps surfacing again in storms or cloud formations. You'd literally become part of the planet. This leads to an interesting philosophical question. On which planet would you want to die, if you had to choose? Venus offers the quickest death, but the most intense pain. Mars offers a relatively slow death, but in conditions that might be less immediately agonizing than Venus. The gas giants offer unconsciousness within 15 seconds, with the destruction of your body happening after you're already dead. If the goal is minimum total suffering, perhaps Neptune or Uranus would be the best choice, if such a morbid ranking makes any sense. You'd freeze and suffocate within minutes, experiencing pain for only about 15 seconds before unconsciousness, and then your body would be destroyed in a process you wouldn't be aware of. But best death on another planet is an incredibly grim superlative. What this tour really illustrates is the extraordinary fragility of human life outside our protective bubble of Earth's atmosphere and magnetic field. We are creatures precisely adapted to one very specific set of conditions: the temperature range, atmospheric pressure, oxygen concentration, and radiation levels found on Earth's surface. Deviate from these conditions in any direction, and death becomes not a possibility but a certainty. Venus teaches us that heat and pressure can kill in seconds. Mercury teaches us that extreme temperature swings and radiation are lethal. Mars teaches us that we need substantial atmospheric pressure and oxygen, not just moderate temperatures. The gas giants teach us that some environments are so alien that the concept of surface doesn't even apply, and death comes from falling forever into increasing pressure and heat. Every one of these deaths reinforces the same message: Earth is precious beyond measure. Our atmosphere, our magnetic field, our position in the solar system at just the right distance from the sun, the presence of liquid water, the complex interplay of geological and biological processes that maintain our environment. All of these factors work together to create the only known environment in the universe where complex life can exist openly, where we can breathe without technology, where we can survive and thrive. The planets of our solar system are laboratories that demonstrate in stark and lethal terms what happens when any of these factors is missing or out of balance. They show us that habitability is not the default state of matter in the universe. It's a rare and precious exception, a delicate balance that must be maintained or it collapses into one of the many forms of uninhabitability we've witnessed on this tour. As we prepare to conclude our journey, let's reflect on what we've learned and what it means for humanity's future as we look to the stars and contemplate our place in the cosmos. We've completed our tour of death across the solar system. 8 planets, 8 distinct ways to die, 8 demonstrations of how hostile the universe is to unprotected human life. From the broiling day side of Mercury to the frozen night side of Neptune, from the crushing, searing hell of Venus to the endless fall into Jupiter's depths, we've seen that our solar system offers no second homes, no easy refuges, no planets where we could simply step outside and survive. This might seem like a depressing conclusion, but it's actually incredibly valuable information. It tells us exactly what challenges we'd need to overcome for human expansion into the solar system. Every place we might want to go, from Mars bases to floating cities in Venus's upper atmosphere to mining operations on the moons of the gas giants, would require complete life support systems, pressurized habitats, breathable air, temperature control, radiation shielding. The technology required is daunting but not impossible. Understanding how each planet would kill us also helps us appreciate what makes Earth special. We're not special because we're at the centre of the universe, or because we're cosmically important. We're special because we're rare. Perhaps incredibly, impossibly rare. In all the planets we've examined, across billions of miles of space, not one offers conditions remotely suitable for human life. Not one has breathable air, not one has survivable surface temperatures and pressures simultaneously. Not one has liquid water on its surface right now, though Mars might have had it in the past. Earth is our only home in a very literal sense. It's the only world in our solar system where we belong, where we can exist without constant technological support. This should inform how we treat our planet. Every environmental system on Earth, every forest and ocean and atmospheric layer, every microbe and mineral cycle contributes to making our world habitable. Damage these systems, and we risk turning Earth into something more like Venus or Mars, a world where we can no longer survive outside our artificial shelters. But this tour also shows us that life, human life specifically, is remarkably resilient within its limits. You can survive for 15 seconds in vacuum, for 90 seconds before death becomes irreversible. You can withstand brief exposure to extreme conditions that would seem instantly lethal. The human body is fragile in cosmic terms, but surprisingly robust in the short term. This resilience gives us hope for space exploration. With the right technology, we can survive in these hostile environments. We can build habitats on Mars, stations on the moons of Jupiter and Saturn, ships to take us to the outer solar system and beyond. Every death we've described today is preventable with sufficient technology. Pressure suits can protect us from vacuum and extreme pressures. Thermal regulation can keep us warm in Neptune's cold or cool in Venus's heat. Chemical scrubbers can remove carbon dioxide and provide breathable oxygen. Radiation shielding can protect us from Mercury's radiation bath. The question isn't whether these deaths are avoidable, it's whether we'll develop the technology and social organisation to avoid them. As we look to the future, to potential missions to Mars, to proposed Venus atmospheric probes, to concepts for mining the asteroid belt or exploring the icy moons of the outer planets, we carry with us the knowledge of exactly what we're up against. We know that space is not a friendly void waiting to welcome us. It's actively hostile, ready to kill us in a variety of creative ways if we make a single mistake with our life support systems. This might make space exploration seem foolhardy or dangerous beyond reason, but humans have always pushed into hostile environments. We've climbed mountains where the air is thin and cold. We've sailed oceans where storms can sink ships. We've explored deserts and polar regions. We've learned to survive in places that initially seemed as impossible as another planet. Space is just the next frontier, the next hostile environment for human ingenuity to conquer. The deaths we've explored tonight aren't warnings to stay home. They're engineering challenges to solve. They're problems with solutions given sufficient technology, resources and determination. Every way to die on another planet represents a system we need to engineer, a protection we need to provide, a failure mode we need to guard against. Our tour of planetary death ends not with despair, but with appreciation. Appreciation for Earth, our only home, the only place in billions of miles where we can breathe freely and survive unprotected. Appreciation for the incredible complexity of the systems that keep Earth habitable. Appreciation for the challenge and opportunity that space exploration represents. As you drift off to sleep tonight, safe in your bed, surrounded by breathable air at comfortable pressure and temperature, protected by Earth's magnetic field from deadly radiation, covered by an ozone layer that filters harmful UV light, take a moment to appreciate how rare and precious these conditions are. In all the universe we've explored, in all the planets we've studied, we've found only one place like Earth, one place where we belong. And if you've enjoyed this journey through the lethal environments of our solar system, consider liking this video and subscribing to the channel for more explorations of science, space, and the universe around us. Leave a comment telling me which planetary death surprised you most or which one you'd least want to experience. And as always, thank you for joining me tonight on this journey through the cosmos. May your dreams be filled with the wonder of space, the beauty of distant worlds, and the profound appreciation for the one precious planet we call home. Sleep well, and remember, no matter how bad your day was, at least you're not dying on Venus.